Hello, and welcome to your Week 10 lecture video. This week we're going to look at the application layer. Now, when we're talking about the application layer, we actually are talking about the application layer in terms of the TCP/IP model, which, if you recall in the OSI model, maps to our top three layers: application, presentation, and session. These work together to provide services for your end user applications, as we're going to see. We're going to look at how peer-to-peer networks work, web and email protocols, IP addressing services like DNS and DHCP and how those work, and file sharing services for transferring files, FTP and stuff like that. That's all in the upper layers. We're dealing with applications. So application, presentation, and session layer maps there, right? It's the top three layers of the OSI model. It's the top layer of the TCP/IP model. It's what's in between and presenting stuff to the user, but in between that and the lower level layers that we've already looked at. Starting at the physical layer, we've worked our way up, right? We started at the physical layer, or layer 1. Then we went into the data link layer, the network layer, that's where our addressing is, the transport layer we talked about last week with port numbers, which are responsible for getting data to the correct application layer protocol. So this provides all of the interface for the applications being used to communicate. And some common ones that you tend to see and use are DNS, the domain name system. Without that, we wouldn't have the internet, right? That maps IP addresses to FQDNs, fully qualified domain names. HTTP, which is used for web pages, viewing web pages over the internet through a web browser, or HTTPS more specifically. FTP, which is file transfer protocol, it's used for transferring files over the internet between a client and a host server. Client, host, server. We've got a couple email protocols up there. POP, Post Office Protocol. The most current version is POP3. And IMAP, Internet Message Access Protocol. There's both email protocols. And DHCP, Dynamic Host Configuration Protocol, which is responsible for giving out or doling out IP addresses to devices as needed. So the presentation layer has three primary functions. It's responsible for formatting the data or presenting the data at the source device into a compatible format that can be received by the recipient device. Any compression that we deal with happens at this way, so the data can be compressed in a way that it can be decompressed at the other end. And it's compression, right? Also encryption. If we're encrypting data for transmission and decrypting at the other end, that happens at the presentation layer as well. So at this layer, that's where our notice all these are file formats, right? MKV, MPEG, MOV. Those are video file formats, right? They actually mean something. They're not just an extension. Just like JPEG and PNG, portable should say network graphics, not NURWork. It's a typo. And then we have the session layer. So that's responsible for creating and maintaining dialogues between your source and destination applications. It handles the exchange of information to initiate those dialogues, keep them alive, and restart sessions that have been disrupted or idle for a long period of time. So lots of things going on. So your TCP/IP application protocols, they specify the format and the control of the information necessary for things we use over the internet. Application layer protocols are used by both source and destination devices during a session for communication. For the communication to be successful, those protocols that are implemented on the source and destination, they have to be compatible, right? That's why we have protocols. That's why we have standards for protocols. So for example, DNS. I already mentioned that maps domain names to IP addresses, so things like cisco.com into an IP address. It uses TCP and UDP port 53, which we talked about last week when we looked at ports. DHCP, Dynamic Host Configuration Protocol. That uses UDP. The client uses port 68, the server uses 67, and that's used for dynamically allocating or assigning IP addresses to devices over the network, and they can be reused when they're no longer necessary. HTTP, that's the protocol that's exchanges text, graphics, images, web pages over the internet. Uses port 80 or 8080 by default. And HTTPS, if you're using HTTPS, the big difference is port 443 instead of port 80. Hopefully that makes sense. And of course, if you have any questions, bring them to the lecture. Or lecture to the lab this week. Now, peer-to-peer networks. Before we talk about peer-to-peer networks, we need to talk about the client-server model, because the peer-to-peer network is kind of based on that, but it's also kind of different. So if you recall, your client and server model, you've got, well, exactly that, a client, which could be a phone or a laptop or a desktop or a smartphone. I said phone and I meant to say smartphone, or a VoIP device or a printer. That's a client. A server is whatever server you're connecting with. Various different protocols that use the application layer format requests and responses from the client to the server. So for example, a web page, right? You type a URL into a browser. It's resolved to an IP address which sends out an HTTP request packet to that web server. The server responds with the HTTP reply, and you get the web page, and it's rendered by your browser because it's written in languages that your browser understands. HTML, markup language. That's how client-server works, right? There's a client, there's a server, requests go to the server, replies come from the server back to the client. In a peer-to-peer network, it's a little bit different. Every single device can act as both a client and a server. They're really common and popular for setting up a centralized network without requiring a dedicated server. So you can do some basic things like file and printer sharing on a common network. Back in the 90s and early to mid 2000s, we used to do this all the time in the form of kind of like a LAN party where everyone would come over, bring their computer, connect everything together at somebody's house, and we'd play a game over the local network using a peer-to-peer network. So with a peer-to-peer network, one computer might temporarily assume the role of server for a transaction, and it could also be the client for another transaction at the same time. So these client and server roles aren't set on a per device basis, but on a as needed per request kind of basis. Peer-to-peer networks are still in use very commonly. They for things other than torrenting, which I'm sure you're all familiar with. They're still in use. They're pretty common. They don't scale very well, but here's a great example of why you might legitimately use one of these. I'm sure many of you are gamers. Blizzard uses a peer-to-peer distribution for their patches. So while they do have both a client and server model as well for their patches, when you first connect to the server, start downloading, you also start downloading your patch or your game data or whatever you're downloading through the Battle.net client from other clients that are connected as well, not just from the server. And that speeds up things and reduces their overhead. It's pretty awesome. So peer-to-peer devices act as a client and server at the same time. Some applications use a hybrid system where each peer accesses an index server to get the location of a resource that's stored on another peer. some don't. Common applications, well, I just mentioned Blizzard, right? And torrenting, right? BitTorrent. Not too sure. I think, well, Freenet's still around. I'm not too sure about Direct Connect. I think Direct Connect's still around. Or eDonkey. But that's peer-to-peer, right? Pretty straightforward. If you have any questions, ask in the lab. So on to web and email protocols. This is how the internet works. When you type in an address into your web browser, that's known as a URL, a Uniform Resource Locator. And it declares how to resolve that resource over the internet by defining it absolutely, starting with the protocol, usually HTTP or HTTPS : // which you don't have to type in. You used to have to back in the day, but you don't anymore. You don't even have to type the www either. That's usually assumed, but www.cisco.com, that's the FQDN, the domain name or server name that's going to resolve to an IP address. And then index.html in this example, that's a specific file, the index page, that exists in document root on that web server. It's known as a URL. So the browser interprets that. It does a DNS lookup to convert cisco.com to an IP address, connects to the server, initiates an HTTP request to the server, which sends a GET request, and asks for the index page. The server responds with the HTML code for the web page, and in that response, in the header, it provides a level 200 status code, which indicates success. The code is sent to the client. It's rendered by your browser, and you see what you see in the browser. Isn't that pretty awesome? So browsing the internet really works. So HTTP itself, Hypertext Transfer Protocol, is a request-response protocol. And it uses three specific messages for communication: get, post, and put. Get requests data from the server. With that, the client or web browser sends out a get message to the server requesting your page. Post is used to upload data to a web server, like data from a form. And what's a form? Have you ever used a form? You have. You may not realize it, but you have. Anytime you've signed up for something on the internet, bought something on the internet, logged in to a service on the internet, or used a search engine, you've used a form. Forms, by the way, can use GET as well. And the main difference is if it uses POST, the data goes in the body of the packet. If it uses GET, it goes in the header of the packet, and you see it in the URL. So the next time you type something into google.ca, have a look at what's in the browser when you get the results. You're going to notice your query up there it's in the URL now with question marks separating it, and that's because the page was submitted, or the form was submitted using GET. Put is used for uploading resources to a web server. HTTP on its own, though, is not secure. It's plain text over the internet, which is why generally we configure HTTPS, right? Especially for sensitive things like banking or checking your grades. You want to always make sure you're using HTTPS. Now, email is a store and forward method of sending and storing and retrieving email or electronic messages. Electronic mail, that's what email stands for, over a network. That's all the internet is, right? It's a network of networks. Email messages themselves are stored in databases on mail servers. Clients, email clients specifically, communicate with the mail server to send and receive email. And there's a couple protocols we use for this. SMTP which is used to send the mail and also communicate between mail servers, and POP or IMAP, which are used for clients to retrieve the mail from the server. We tend to use IMAP now because it works better with mobile devices. POP does not, but I mean, it could be out there. When a client sends email, the client SMTP process connects to the server on port 25. And after that connection is made, the client attempts to send the email to the server over the connection. When the server receives the message, sorry, bad on that's telling you someone came online. When the server receives the message, it places it in a local account if the recipient's local, or it forwards it to another mail server for delivery. The destination mail server might not be online, it might be busy, so if that's the case, it will spool the message to be sent later. Note these message formats require a header, the recipient email and sender address, and a body. If it doesn't have that, most servers are configured to just discard it. Now, an interesting thing about SMTP, before I move on, many people don't know, communication between your client and server using IMAP and POP, that can be encrypted. But communication between email servers on the internet is not encrypted. Kind of crazy when you think about it. POP, I'm not going to spend a whole lot of time on POP. It stands for Post Office Protocol. The most recent one is version 3. And it's an application to retrieve mail from a server. So when you download mail from a server using POP, the messages are deleted from the server because they're now locally on the client. That's one reason we don't use it anymore. It uses port 110. It establishes a connection with the server. They exchange their commands and responses until that connection's closed. We don't use this anymore, partially because once those files are gone from the server, they're gone, right? Once your email is pulled down from the server to the client, it's no longer on the server. I mentioned that's one reason. The other is when you connect as a client to a POP server, it downloads everything. That would be hell on your data plan. So we don't do it that way. We use IMAP, which works a bit different, as we're going to see. IMAP, or Internet Message. I've messed up the acronym already. We talked about it earlier. It's another protocol for retrieving email. Unlike POP, when a user connects to an IMAP server, copies of the original message are downloaded. The original ones stay on the server until they're manually deleted. And when you connect with a device and say you refresh your client, so it pulls all of it in and populates your inbox with unread emails that you do a couple times a day, it downloads only the headers. It doesn't download the body of the email until you open an individual message. So it's a lot more friendly on bandwidth. Now, when a user deletes, get rid of that annoying thing, deletes a message, the server synchronizes that action and then deletes it on the server. So you can delete it from the client and it'll be deleted on the server as well. So that's email. Now we're going to look at IP addressing services, which we've talked about a little bit already, but we're going to talk about a little bit again in some cases. We talked about DNS, right? DNS is the domain name service that's responsible for converting IP addresses into domain names, fully qualified domain names, FQDNs. So you can remember to type into a web browser cisco.com instead of that long IP address on the screen, and it's even worse with IPv6. The protocol itself defines an automated service that matches resource names with a record that has that numeric address. It also includes the format for queries, responses, and data. A DNS server stores different types of records that are used to resolve names. These names could contain, do contain, the name, address, and type of record. Some of the records that you're going to see are A and quadruple A records. A records are used for IPv4. Quad A or quadruple A are used for IPv6. NS, those are the name server records, and that specifies who the authoritative name server is for the zone. And MX records, those are used to list email servers, the servers that are responsible for dealing with your domain's email. When a client makes a query, the DNS server process first looks DNS process first looks at its own records to try to resolve the name. If it can't resolve the name using the records it's stored, it contacts other servers to resolve the name. And once a match is found, it's returned to the original server, and it's cached there just in case you go and check it out again. So if you type in cisco.com and then your friend does the same thing a minute or two later, it's already going to be cached locally. It doesn't need to go through that recursive lookup process. DNS uses the same message format between its servers, and these consist of a question, answer, authority, and additional information for different types of client queries and server responses. Question is just the question for the name server. Usually, hey, do you know the IP address for such and such, cisco.com or whatever? The answer is the server's response to a question. And it will reply with, yes, I do, and here's the resource record information. Authority is when the server says, I don't know, but this server over here, he knows, go talk to him. And additional, those records hold additional information, such as the mail exchange record, right? The who handles the email for our domain. That's what MX records have in them. Now, DNS uses a hierarchical system to create a database and provide name resolution. Each DNS server maintains a specific database file, and it's only responsible for managing the name to IP mappings for that small portion of its DNS structure. When a DNS server receives a request for name translation that's not within its own zone, it forwards it to another server with the proper zone for translation. DNS, everything descends from root, just like the Linux file system. There's a lot of similarities here. The root domain is actually represented by a dot at the end of the FQDN, which we don't have to put into a web browser anymore. But once upon a time, like 30 years ago, you did have to do that. And if you didn't, it would fail. You used to have to put in the http:// whole thing, www. whatever, with the dot at the end. I'm glad we don't have to anymore. It was a nightmare. Below root, all of the TLD, the top level domains, exist. So .com for company, .au is a country top level domain. It's Australia. .ca for Canada. .us for the United States. .net short for network. .edu for education. There's a whole bunch of these, and in fact we're coming out with new ones all the time. Then you've got your second level domains. These would be things like cisco.com, centennialcollege.ca, right? The company itself. Now within there, you're going to have subdomains. For example, www.cisco.com. That maps to a web server, or more probably to a load balancer that balances the traffic between a bunch of web servers. ftp.cisco.com, that's going to be an FTP server, a file server, right? Mail.cisco.com, that's going to be, well, a mail server. So DNS is one of those things that just, it makes the internet work. But to make it handy for troubleshooting, you can look up queries and query DNS servers from the command line using a tool like NSLOOKUP. NSLOOKUP is a utility that you can use in any operating system. It allows you to manually query DNS servers to find out if they've got records configured. This is usually used when you've configured DNS and you want to make sure it's working properly. So for example, go open a command prompt, type NSLOOKUP, and then you're going to type www.cisco.com, and I think you're going to do this in the lab. You'll see it's associated with a couple addresses, an IP version 6 and IP version 4, its name, its server address, and the server it's with, right? And aliases. In this case, its name is actually origin www, its alias is www. Alias allows you to map one name to another record that already has a name. And you can just quit this at any time by typing, I think it's quit, it might be exit. I always get it mixed up and type the wrong one invariably. You can continually look things up in this until you're done, then you just get out. Hopefully that makes sense. I'm going to pause for some water. So DHCP, Dynamic Host Configuration Protocol, we talked about in the previous lecture, right? It's for automating the assignment of IPv4 addresses, subnet masks, gateways, and other network parameter like domain names without your organization or throughout your organization. For IPv6, use DHCP version 6 instead. DHCP is referred to as dynamic addressing, where your devices get their address kind of, well, dynamically. I was trying to not describe it using the word dynamically, but it's just not working. Static addressing, that's manually entering the IP address on every device. And you can understand why you wouldn't do that in a network outside of maybe your servers. When a host connects to a network, a DHCP request is sent out, contacting the DHCP server, and it requests an address. The server chooses an address from a configured range of a pool called a pool, and assigns it or leases it to a host. They don't get to keep it. Many networks use both DHCP and static addressing. DHCP is good for hosts like client devices, printers, well, not printers, desktops, laptops, tablets, things like that. For things that you want to be able to find guaranteed, like printers, servers, routers, switches, you're going to use static addresses. Alternatively, in a small network, you might use DHCP reservations for some of those things, but maybe not all, where you actually set up you map a MAC address to an IP address in the DHCP configuration that says, hey, anytime this client requests an IP, give them this one. I've done that at home with my wireless, or my wireless, it's wired network printer, because I'm just lazy and it gives me a centralized place of administration. And if DHCP is down internally, that's the problem I'm fixing. That's why I've always done it that way. Now, DHCP uses the 4 packets. When the client first boots up and connects to the network, client broadcasts a DHCP discover packet over the network. This goes out to any DHCP server on the network. The server will reply with an offer, which offers a lease to the client. If the client receives more than one offer from multiple network or DHCP servers on the network, it has to choose. The client then sends a request, formally requesting the IP that it's chosen, and the server responds with an acknowledgement, and the lease is finalized. If the offer is no longer valid, then the server will respond with a DHCP negative acknowledgement, or NAC. DHCP v6 works kind of similar, but it has different messages, and, well, the whole thing's just a bit different. Good lord, Lots of people playing games tonight. Not me. So file sharing. There's a variety of file sharing services that we use regularly. FTP being one of them. Usually use SFTP, which is actually an extension for the SSH protocol. FTP was developed to allow you to transfer data between a client and a server. Usually for web development, you tend to use this a lot because you'll connect to a server and upload your files from a local thing to the server. Or you just use Git and GitHub and pull them in. It's a different way of doing it. FTP uses 2 ports, 20 and 21. The first step for your connection, the client establishes a connection using port 21. That's used for your control traffic. So that traffic consists of your client commands and server replies. Port 20 is the other port that FTP uses, and that's where the actual data transfer occurs. That connection on port 20, that's created every time data needs to be transferred. Port 21, that one stays open until you're just done and you disconnect. Data transfer with FTP can happen in either direction. You can download or pull data from the server, or upload or push data to the server. Also, FTP is plain text over the internet, so we tend to use SFTP because it's secure. We like secure, right? SMB, or server message block, that's a client server request response file sharing protocol. Servers make their own resources available to clients on the network. It's actually commonly referred to as Samba, S-A-M-B-A, oh, it's SMB, it's the underlying protocol, and it's used for file sharing between Windows and literally any other operating system. So if you've got a MacBook, you want to share files at home with your Windows device, you just set up a Samba share on your MacBook and you're good to go. There's 3 functions for your SMB messages. They're used to start, authenticate, and terminate sessions, control access to files and printers, and allow applications to send or receive messages to or from other devices. Unlike FTP, with SMB or Samba, clients establish a long-term connection to the server. In fact, you can map a network drive using Samba to your local device and access files on it as if it was locally on your device, provided you're connected to that network. Once your connection is established, the user of the client can access those resources as if they're local, and you're good to go. And you can share printers this way too. Isn't that awesome? And that brings us to the end of this chapter. Normally I do some subnetting, but it's been a long day. We'll do some more subnetting in the lab this week if you so desire. And I guess next week we will do some additional configuration, or we'll try to get some in, subnetting and configuration. So thank you for watching. Take care. Be safe. See you in this week's class. Bye for now.